Hello, everyone. My name is Mikhail Shalaginov, and today, on behalf of our research team, I would like to present our results on reconfigurable metasurfaces and specifically on the reconfigurable parfocal zoom metalens. Zoom lenses are widely employed in numerous applications spanning in photography, cinematography, computer visions, biomedical imaging, and many other fields. Conventionally, zoom function is exemplified, as you can see here, by a stack of refractive lenses where one or more of the lens elements move along the optical axis. So this movement changes effective optical length, causing change in magnification. Ideally, it should be done without any focus readjustment. The main drawbacks of such approach are increased size, weight, complexity, reliability, speed. So the zoom lens can be actually implemented via taking another route by using metasurfaces, which represent themselves flat optical components that can control phase, amplitude, polarization, and other properties of light. The metalens path will lead to zoom metalenses that are more compact, superior in performance, and without containing any mechanical parts. So multiple works showed varifocal metalenses by leveraging various mechanisms, including substrate stretching, MEMS actuation, phase transition in materials, thermal optic effect, and switching polarization states. Our group also recently implemented high-performance varifocal metalens by leveraging transparent phase change chalcogenide alloys. So our group recently developed a new material, germanium antimonide selenium telluride, which we briefly call GSST 421, with unique optical properties. In addition to high refractive index and refractive index contrast between amorphous and crystalline state, this dielectric material is also highly transparent in broad IR band for both amorphous and crystalline states. If we compare now it to the conventionally used alloy GST-225, the figure of merit, which is defined as the ratio between delta N to K, so the GSST will have this figure of merit about 100 times higher. So this is primarily due to substantially reduced losses in crystalline state. So based on this material platform, we first demonstrated a varifocal metalens functionality, which schematic is illustrated here. So the GST pattern has been defined on one side of a transparent substrate. So when GSST is in amorphous state, colored in blue, the incident light is focused in a focal plane f1, 1.5 millimeters away from the surface of the metalens. Afterwards, if we switch GSST to crystalline state, now showed with red color, the material, the focus spot will move to position f2, which is 2 millimeters away from the metalens plane. How did we implement the focus spot shift? We have accomplished this by switching between the two phase delay maps, which are illustrated here. So the colors stand for various phase delay values. So the reconfigurable is achieved by changing the refractive index of all meta-atoms collectively. Each meta-atom acts as a phase delay pixel toggling between the two phase delay values. Ultimately, for realization of this bi-state varifocal metalens, we used 16 distinct meta-atoms geometries, which you can see here. And these geometries have enabled the required phase delay values switches. We have fabricated the metalens, then characterized and demonstrated high resolution, low crosstalk imaging. Here in the imaging demo, the metalens, first in amorphous state, produce clearly resolved image of the resolution chart with a half period of 7 micron, which is close to the diffraction limited resolution. And this image has been obtained in the primary focal plane and no image is observed in the phantom focal plane. The same results were obtained for the metalens in crystalline state, where now the primary and the phantom focal plane got flipped. Additionally, we further showed that this kind of metalens can be used for imaging multi-depth objects. Here we had two substrates rotated by 45 degrees in respect to each other. And this multi-depth imaging has been achieved with diffraction limited resolution and minimum crosstalk. Now, we have capitalized our prior varifocal lens advances for constructing a parfocal zoom metalens. Overall, the optical zoom functionality has been largely remained unexplored in metasurface system. A number of so-called zoom metalens have been implemented, although they're in fact varifocal lenses, whose focal plane constantly shift as the lens reconfigures. A true zoom metalens must be parfocal. In other words, the position of its focus plane must remain stationary when its effective focal length is changed. A parfocal zoom metalens design was first theoretically conceptualized by Zhang et al. In 2017. However, the design only affords a small zoom ratio. Moreover, no parfocal zoom metalens has been experimentally demonstrated to our knowledge. So here, in our case, the parfocal zoom metalens is considered as the metasurface doublet. The metasurfaces are color-coded with blue color for amorphous state, and red will be in crystalline state. So these two metasurfaces can be fabricated either on the opposite sides of a single substrate onto separate substrates. Each metasurface encodes two different phase maps corresponding to two zoom states. In the wide angle mode, which is related to GSST being in amorphous state, the central part of the top metasurface serves as the negative lens, which expands the incident beam to a larger width on the bottom metasurface. And then the bottom metasurface acts as the positive lens to form the image. In this case, the lens has a small effective focal length to accommodate a large field of view. Now, if we go to a different regime, which we call a telephoto mode, the top metasurface functions as the positive lens, which focuses the incident light beam to a smaller area at the bottom metasurface, and the bottom metasurface instead becomes a negative lens to realize a large effective focal length. Then, of course, in respect to the wide angle mode, while maintaining the same parfocal length. And the switching, again, here between the two modes has been achieved by collectively changing the material of both the metasurfaces. Here is a more detailed architecture of the parfocal zoom metalens. It has been designed for the mid-IR wavelength range, mid-IR wavelength of 5.2 micron. In order to achieve a zoom of 10x, the wide angle mode should have a field of view of 40 degrees. And for the telephoto mode, 4 degrees, with a corresponding effective focal length of 1.3 and 30 millimeters. The metasurfaces pretty large, about 3 and 4 millimeters in diameter, with illustrated phase maps. A key feature of the design enabling a large zoom ratio is that the front metasurface also acts as the variable aperture, which is outlined here with the green circle, which scatters out the undesired light, which is, of course, outside of this aperture area, to the substrate propagating modes. These are depicted the intensity profiles of the expected focal spots in both modes for normal and peripheral beams. As you can see, they are of high quality and diffraction limited. To effectively realize the design phase maps, we performed a thorough search of this meta-atom library or meta-atom geometries. The final meta-atoms were selected by maximizing this figure of merit which includes both transmittance of each of the meta-atoms as well as the phase error, delta phi. Here you can see the table of the meta-atom geometries, the top view sorted by phase delays in amorphous state and crystalline state. The polar diagrams illustrate simulated phase spreads as well as amplitudes corresponding to the transmittance of the 16 meta-atoms in the two material states, enabling the required phase delay switches. Here are the images of the fabricated zoom metalens components of decent quality. The focusing performance of the lens was measured using the demonstrated setup, a 5.2 micrometer collimated laser beam incident at various angles ranging from -20 to 20 degrees in the amorphous state and -2 to 2 in the crystalline state. Focal spot images were magnified using a relay lens assembly and projected onto a liquid nitrogen-cooled indium antimonide focal plane array. The recorded focal spots are nearly diffraction limited and serve as a verification of designed field of use and the target 10x zoom ratio. Following a similar approach, we also implemented a polarization-multiplexed zoom metal lens in the visible range at a wavelength of 670 nanometers. The meta-atoms were represented as rectangular shape, possessing two distinct responses for vertical and horizontal polarizations. The experimental demo of the zoom imaging functionality has been performed on the USAF resolution chart patterns. The top image has been obtained for the wide angle regime, and the bottom ones are the zoomed in or telephoto images in the telephoto regime. There are three takeaway messages which I would like to bring to you. The first one is that we have proposed a non-mechanical zoom metal lens architecture, which offers large zoom ratio. Here it has been demonstrated 10x, negligible distortion and diffraction limited performance. The two zoom metal lenses were developed and experimentally realized using phase change material platform for mid-infrared wavelength and polarization-multiplexed platform for the visible range. So this versatile zoom metal lens platform features a compact form factor, excellent image quality, and non-mechanical actuation. Thereby, we foresee that this new technology will be highly implemented in various fields of optics, including microscopy, sensing, imaging, image projections. I would like to thank all the contributors to this work, specifically, as well as the sponsors. This work has been supported by DARPA Extreme program, led by Rohit Chandrasekhar, and you can find more details on this research work in our paper at Advanced Optical Materials, which will come out soon